Yeah. So now let's talk about absorption, right, and stripping. Yeah, absorption is one of the common processes. It can also be called scrapping, right? So we are trying to move a component from a gas, which we try to use a non-volatile liquid, right, in contact with or how to call the absorbent or the solvent, right, to remove a component from a certain gas, right, a gas mixture, right. So the one we call the dissolvation, which is the stripping. That one we remove a component from a liquid by using hot and insoluble gas stream. Right? So they are opposite to at operation, yeah, unit to at operations, right? So here's an absorption column where we have the gas flows inside, right? The liquid flows, it comes into contact, right? It removes the component that will be removed. Then the clean gas comes out over here. Then the liquid with the component comes out over here. Then the stripping too, the gas comes, the liquid comes. So this liquid coming in, the gas gets into contact with the liquid, it removes what it wants to remove and comes here. The the clean liquid comes out also over here. As you can see over here, absorption and stripping column they go together. Right. So for gases to be removed, right, we need some common targets or some things that we can be used to remove them. So if in terms of ammonia manufacture, where I want to remove these gases, right, the common targets that I want to mostly is to get less than 16 ppm of carbon dioxide in that ammonia, right, and you know that absorption is a physical. We have a physical absorption, right? So as you can see, if you have CO2 and water, right, you can have this. You can also have all these things. They are all physical absorptions, right? In the chemical absorptions, right? You can have all these things also to be parts of them, right? And over here, if you want to determine the should I say the phase equilibrium, so if you want to determine the number of phases, right? Or if I want to determine the degree of freedom, like the variables here. Over here, you can see that absorption column, right? So we label this part as B, then the top part as what A, right? So this is the gas entering, having its mole fraction, right? This is the liquid also entering, also having its fraction. Then the gas leaving, the liquid leaving. So over here, they will come into contact, right? So where this liquid, right, will take out something from the gas, right, a component from the gas and come over here. Right, so doing overall balance in equal out, right? So LA plus LB, VB equal V plus that LB. And if you want to do a component balance on just the solutes, right, it becomes multiplying them by their fractions, right? And that will end up. So if you have a component balance at any of the column, in any point of the column, right? Since we're talking about this one, we have in this one too, right? That's the generally, yeah. Then the slope, right? The slope of the operating line is what? L over V. So we just have to take note of it, right? The slope of it is what? L over V. Now, one thing you have to also notice that if you have dilute mixtures where we are having, that means that you have less than 10% of soluble gases in there, right? You will be having the operating line over here. So mostly the operating line is on top of the equilibrium line when you're talking about absorption. When you're talking about stripping, the operating line will be below at the equilibrium line, right? The equilibrium line. So this is an example. So this is the equilibrium curve, right? And based on these things, when we have operating line, that's 4 times. So this is the 2 times. This is where we have the normal one, right? And you have to call the driving force, right? So this is the driving force. That's the y minus one, so y star. Right? It becomes what? The driving force in the system. And over here, you should be able to also know this one that we have a minimum rate, right? Or you can have a maximum rate. So this is absorption. So if you want to determine the number of stages, right, we start from the bottom here. And so this is the operating line, the equilibrium curve. This is the operating line, right? So you start from here, then you move it like that. So each full triangle becomes what? One stage. So this 1, 2, 3. So this one is 3 point something too. The shortest way, have a shortest way to get it. So you can complete your triangle here. So if you complete this triangle, you use your ruler to take the full measurement. So let's say the full measurement is let's say 8 centimeters. Then use the ruler to take just this small portion, which let's say gives me 1 centimeter. So it becomes the small 1/8. So one centimeter 1/1 centimeter divided by 8. So 1 divided by 8, which is 1 divided by 8, which is this one becomes 0.125. So that means that I have 3.1 stages, right? Yeah, so that's the also a shortest way to do. So just complete the triangle. Take a ruler to measure the whole thing, right? The hypotenuse of the thing. You get it down. Then you measure just the small portion that you have. Then you divide the small one by the bigger one. Whatever you get, you add it to your full complete stages to get the actual number of what stages for this one. So this is the number of stages, right? So this is for stripping. So the operating line is below this one. That one too, right? We we start right. So we start from here. I start from here. You can start from the top, right? So one, that one to the same thing. You can complete a triangle and you also do it, right? Now, if you check for this question, then one thing you should know also is about when you talk about a solid free situation, right? So when you talk about a solid free situation, you mostly be using these ones, right? So we have the move fractions, right? And so we're talking about these ones, right? So when you talk about solid free situation, that means you're using um the mole ratios, which is the big one, instead of the mole fractions, right? Solid free situation. That makes the question much easier for you to solve, right? And the small ones are the mole fractions, right? Which mostly will be given to you in the question. And you can also have this one when the L over V is at the minimum, then we'll be having this one, right? So that makes our equation very easy, right, to solve for everything, right? Yes, and for the solid free situations, right, we need to find the liquid and the we need to find the liquid flow rate and the volume and the gas flow rate, right? So when talking about solid phase, which is L prime and V prime, right? So the L prime becomes the L, then 1 minus what XA, then this one becomes V, 1 minus what YA. Right? So basically, yeah, so that it's easier for you to solve the questions this way, right? Yeah, so this stripping, as I said, stripping. Mm. Yeah, so if you check this question, you can see. Okay, so let's go to where you have a packed column, right? Then you have a packed column. So when you have a packed column, right? So you have a packed column. That means that you should be able to get in what you call the HOI, then what you call the what NOI. So the number of transfer units and what height of what, then the height, right? And over here, as you can see, you have the height of the tower, which should be given by height of transfer units and the number of transfer units, right? Which is this one. So the V over A, right? The V over A, as it is the height of the tower. So you try to obtain these two, right? Then we multiply these two to actually get the height of the column, right? So this is the gas film. So if you have just the gas film situation, then you use the KY because that talks about the constants in just the gas film, and you have the V over E, right? The V over E, which mostly they represent by these. That's in the gas phase. So this for the gas, we use GM to represent the V over E, right? Then L over A, you mostly use the LM to represent that one too, right? And if you have the overall, that's where the big. So if you have the HY and you have the HOY, that's for the overall gas phase. So you need a big case, right? And if I want to evaluate the NOY, we use this equation, right? But what will help us in developing that equation is using the log mean, right? So use the log mean, right, to evaluate that one. So you just need to do YB minus YA divided by what? The log mean. Then you have XA minus XB also divided by the log mean. it'll be much easier for you to calculate for the NOY and NOx. So this is what I was talking about, the flux, right? So V over E and L over E. So mostly sometimes when the question is given, you'll be given the V over E straight away, so that one day you are cool. But sometimes they just give you the V, which is not V over E. So you just take note of the question very well, right? Yeah. Then this one was also a relation that when we are looking at the interfacial mass transfer, we look at some of these situations, right? So we looked at this equation when you're looking at that one. So multiplying through by G in such a way that I'm making sure that I get the mass fluxes in there, right? Right. So this one becomes my HOI, right? If I need anything HOI, then this becomes my HOX. Very easy to solve, right? So if you look at this question where they said find NOY, HOI, and all those things over there, right? So you can see that I'll have something like this. Right? The gas enters, the gas leaves, it leaves, right? So I told you I'm labeling here B, and this one was E, right? So you see that the XE, right, was 0, but they gave me an LE of 0.30 um 9, right? But you see this one over here will be what the LM, right? Because it's an L over E, right? It's an L over E. Then for the gas, they said that my VB is 0.0617, right? Then I'll have my YB is 0.03, and they told me that the column removes 99%, meaning that only 1% will come out over here for the component. So YA will become what? That the YA that will come over here will be 0.03. So only 1% of this. So 1% is what? 0.1, 0.01, that's 1%, right? And I have 0.123 and 0.003. So that becomes YE. So that the question will be much easier for me to solve. And this is XB. I don't know XB. Right. And since this one, the percentage, the thing over here is 3%, which is less than 10%, meaning you're talking about a dilute situation, right? So here, when I have inward, so I have VA, VBYB plus LAXA being equal to being equal to VAYA plus XB right? So based on this equation, and I put in my V's, right? So so I have V, so I have YB minus YA being equal to L, XB minus what? XC, right? So XB minus XC. So over here I have L over V being equal to L over V. So L over V being equal to um yeah, so let me just put this over here. So the V over there was given as 0.309. Then my YB, which is 0.0003 minus sorry, my YB is 0.0003. Then my L was given as, so let me clean here, write it again. So I clean this one. My V 0.0617 and 0.03 minus 0.103 equals 0.309. Then XB is the one I'm trying to find, minus 0. XC is 0 because here was a pure liquid, right? It's a pure solvent we are using. So XB, when I calculate, gives me 0.00593, right? So I need XB before I can even continue to think of finding NOY and NOx, right? So if I get that one, then I should be able to, and so that you even find the total resistance too. So based on this one, right, Based on this, then I can actually also go on. So I'll be using 1 over KYA will be equal to 1 over KYA plus M divided by KXC, right? So I'll be using this one, right, to find the big one, right? I have the small ones. So if I use that one to find the big KYA, I'll be getting 0.0829. Right? That's what I'll be getting for the big KYA. Okay, so I'll be getting this one. Right? And the unit becomes what mole per meter square second, right? Yeah, the unit is mole per meter square second. Yeah, that's the big KYA. And you see, they told us to find some um what percentage of the total resistance in the gas phase, right? So if I want the total percentage of the thing in the gas phase, that one becomes the small KYE divided by the total resistance. So the total resistance is 1 over the one due to the gas phase, the one due to the liquid phase, then times 100%. And so the resistance is 1 over this one. So if I use this one, I can get the percentage that's actually just in the gas phase, right? So yeah, in the gas phase. Yeah, then we have that relation to there. So from here, you can actually get HOI, right? Which is the question wants HOI, which is GM divided by QIE. So we have QIE to be 0.089, right? Then GM was given, of course. Yeah, GM was given as 0.0617, right? GM was given in the question. So then we divide this one by 0.0829. So that gives us a HOI, right? So if we get our HOI, then we find our NOI, right, which is YB minus the YA divided by log, right? So we use this one to also find the log, right? Then you come and put it over there. Then if you put it over there, we multiply these two to get what? The height of the column, which is the ZT, right? Then if I want to also get my HOX, right? So I say HOX2, which is also LM divided by KLE. So I need to also find KLE. So I use the relationship between KLE and KYA. Also get that one. Then my NOX, right, also becomes my XB minus XE divided by, so the log, right, so the change in XLM, right, the log mean, right. So I have all those things to consider, right. But in a case that I'm not giving the GM and like all those things, then you have to opt for the HOY being equal to HY plus M, that long formula, right, so that I can be able to solve this question. Yeah, so you can be able to solve this question. Yes. Then yeah, and this question was also very simple, which is a stripping column, right? So having this stripping column to give us the partial pressure. So they say P of toluene is equal to 256 x, right? So if I want to find, and I always see, so it's partial pressure of toluene divided by the total pressure. So if I put this one over 256 x, total pressure was 1.1 atmospheres, right? So 1.1 atmosphere. This one will land me 232.7x is the y. Yeah, so I get it in terms of this one for the equilibrium, right? Then mostly becomes very easy for me to solve because they are telling me to determine the minimum air rate in millimole per minute for a water rate of 100. So you just have to draw your this thing, right? But you see over here, if I draw this one, right? So this one is entering, this is leaving, this leaving. Right, so this is the gas, this is the liquid that's entering, right? But the liquid that's entering, you want to reduce it from 60 ppm, right, to 2 ppm. And so you have to convert these ppms to what? Mass fractions, right? So you get them in terms of mass fractions. And you are talking about water and what? Toluene, right? So your water contains 60 ppm toluene. So you're talking about toluene, right? And water. So you try to get the mass fractions. This 60 ppm, 2 ppm in terms of mass fractions. Then we can write the balance around the whole thing, the component balance, right? You have the component balance there. You can use that one to find the minimum at a rate. Where is the V minimum? Right? Where is the V minimum? And so we can also sometimes we have a formula that we use that we have the L over V, right? Minimum, right? Which should be equal to what? The M. The M over, so you use this one, can use this one to also find the V minimum. So this is when you're talking about the pinch at the bottom, right? So the pinch point, right? So when the pinch at the bottom occurs, right, this equation is valid. So you can use this equation to actually calculate for the, so the V minimum would be L divided by M. That's also a simple way to go about it. And also calculate for NOx for an air rate twice the minimum, right? So if I get the minimum, right, so if I get the minimum, so twice times the this one, and I use that one, then they're asking me to find the NOx. Right? So you know how to find NOx, right? It's using the X. So if I have the X's, right? I have XC and I have XB. So I have to, so I get my NOx, which is XB minus XC over the log this thing, right? So we try to also find XA and XB, but using that one, we try to get this also one in terms of